Hello everyone, I am Myungsuk Kim from Seoul National University in South Korea. Today, I would like to present our work, RealWear, Improving Performance and Lifetime of SSDs using a NAND Aging Marker. In this presentation, we introduce new NAND Aging Marker that can accurately estimate the wear status of NAND block. Here is the outline of this talk. I will first introduce how NAND flash memory wear out, and I will review the inadequacy of the conventional P cycle-based NAND aging marker. This is a schematic of a 3D VNAND cell. By injecting electrons from substrate to silicon nitride layer, NAND cell increases its threshold voltage, which is called program operation. On the other hand, NAND cell decreases threshold voltage by removing electrons from silicon nitride layer, called erase operation. NAND cell can have different threshold voltage by injecting different number of electrons so that it can store or represent different bit data. To program or erase NAND cell, a high operating voltage, more than 20 volt, is required. This high operating voltage damages the tunnel oxide, thus generating traps or defect in the tunnel oxide. If the traps are accumulated by repeated program and erase operation, we call it P cycles. NAND flash memory wears out. To explain the wear mechanism of NAND flash memory more easily, we compare NAND flash memory with paper. NAND flash memory is similar to paper. We can write on the paper and read what we wrote. And we can also erase what we wrote. These are very similar to NAND operations. When you write and erase repeatedly, paper is worn out, and it cannot be functioned as a memory. Similar to paper, when NAND flash memory experiences repeated write and erase, it is worn out. Since the wear of NAND blocks is the key factor to efficiently manage the flash-based storage systems, it is essential to know the exact information about the wear status of individual NAND blocks. The most common wear indicator is to count the chronicle age of a NAND cell based on the number of program erase cycles. Is this conventional P cycle-based NAND aging marker sufficient to accurately indicate the wear status of NAND flash memory? We investigated the lifetime of each NAND blocks varying P cycles. Our evaluation results reveal that some blocks are able to withstand a larger number of P cycles than others before becoming unusable. For example, some NAND blocks showed uncorrectable errors at 8,000 P cycles, while others were still usable after 16,000 P cycles. In addition, NAND bit errors are significantly different even at the blocks with the same P cycles. Furthermore, P cycle-based NAND aging marker cannot reflect I/O workload characteristics such as dwell time. Dwell time is defined as interval time between consecutive erase operations. Therefore, we can conclude that conventional P cycle-based NAND aging marker is not sufficient to indicate the wear status of individual NAND blocks. P cycle-based NAND aging marker is similar as the chronicle age of a human being. He is a very famous soccer player. Although his age is more than 30, his biological age is about 20. This is me. Although my age is 45, by biological age is secret. This difference is caused by a genetic factor, for example, telomere. Similarly, in NAND flash memory, each NAND block can have different aging characteristics because of process variations. Although the genetic characteristics is the same, for example, twin, human can exhibit different aging characteristics due to lifestyle or living environments. Similarly, in NAND flash memory, each NAND block can have different aging characteristics because of different operating conditions. Next, I will introduce how we design a new NAND aging marker, RealWear. Our goal is to design a new NAND aging marker that accurately indicates the wear status of individual NAND blocks. If our NAND aging marker were on idle, all NAND blocks would reach their maximum lifetimes at the same point. To reflect various factors that affect the wear of NAND blocks, we design our new NAND aging marker, RealWear, using multiple variables that are closely related to the wear of NAND flash memory. RealWear was created in two steps: variable selection phase and building model phase. Each variables are carefully selected based on experimental results using real state-of-the-art 3D flash chips. And we implement RealWear using regression model. Especially to determine the wear degree of NAND blocks, we use the retention bit errors after the maximum P cycles. We investigated which variables were related to the wear status of NAND blocks or not. 10 candidate variables are examined. Among variables, program latency is excluded because it is not correlated with the wear of NAND blocks in high endurance region. In addition, although random telegraph noise is well correlated with the wear of NAND blocks, it cannot be included in our model because it is difficult to measure online environment. As a result, we selected 5 variables for our model. RealWear is constructed using multiple online measured variables, and RealWear is calculated based on the regression model. We verify the effectiveness of our model RealWear by comparing it with the evaluation results for inadequacy of P cycle-based NAND aging marker. We checked 3 items: how accurately it can estimate the lifetime of its NAND blocks, how effectively it can reduce the error variation between NAND blocks, how well it can reflect the effect of operating conditions on the wear of NAND flash memory. We first compare the estimation accuracy for lifetime between NAND aging markers. Unlike P cycles, if RealWear were used as a NAND aging marker, most blocks reached their maximum lifetimes at the same value. To further analysis, we compare the accuracy of lifetime estimation between NAND aging markers using a new metric, life. Life was defined as the ratio of predicted total amount of writes and actual amounts of writes. P plus and P++ are other P cycle-based NAND aging marker that are designed using P cycles, program latency, and RealWear. RealWear showed superior accuracy over existing NAND aging markers. Unlike P cycles, NAND blocks with the same RealWear values exhibit almost the same number of bit errors. Furthermore, unlike P cycles, RealWear properly reflects the impact of I/O workload and the temperature variation on the wear of NAND block. Next, I will talk about experimental results. In order to evaluate the effectiveness of the proposed model, RealWear, we have implemented the RealWear Aware FTL, called rful, on a flash emulation environment. And for evaluations, we used 6 different workloads which have different read-write ratio and WAF. We identified the advantage of our RealWear based on 3 case studies. First, we measure the total amount of writes until an SSD reaches the end of its life. In general, the lifetime of TH flash is determined as 1,000 or 8,000 P cycles depending on its target applications. rftl can serve more writes over the baseline FTL because it can fully exploit the lifetime of its NAND blocks. RealWear can also maximize the effect of the existing optimization techniques of flash-based storage. In this case, we apply RealWear to fast copy technique that improves the performance of flash-based storage by using internal copyback operation. When RealWear is used as a NAND aging marker, we can more utilize the copyback operation. For example, we can use copybacks 5 times, while the P cycle-based technique can apply copybacks at most 3 times. By using more copyback operation, RealWear can improve the flash performance by reducing the GC overhead. Finally, RealWear can open the new opportunities to optimize the flash-based storage. To minimize the fluctuation in read latency, we try to apply the optimal read reference voltages, which are provided as a predefined lookup table, depending on the wear status of NAND blocks. We created 2 optimal read reference voltages table we called ORT. One is ORT using P cycles, and the other is ORT using RealWear. When we apply the ORT made using RealWear, no blocks need more than 2 read retries, regardless of the data retention requirements. Therefore, rftl can bound the read latency within 3 TR, 3 read latency, even at the end of lifetime of NAND flash-based storages. Let me conclude my presentation. We show that the conventional P cycle-based NAND aging marker is not sufficient to indicate the wear status of NAND flash memory because of process variation between NAND blocks and the different operating conditions. To overcome the limitation of the conventional NAND aging marker, we presented a new NAND aging marker, RealWear, using multiple variables and verified its adequacy by comparing it with other existing NAND aging markers. We also showed that RealWear can efficiently improve the lifetime and the performance of flash-based storage systems. Our work can be extended to various aspects. For example, NAND aging marker can be designed using machine learning technique. In addition, real-time SSD can be developed using bounded lists. We encourage you to read our paper for more details. Thank you.